Okay, we should be live. Hi, everybody. This is January 8th, 2025. This is episode number 5 of the Physics of Bitcoin. And I am here with my co-host, Stephen Perrenot. And we are going to discuss some in-depth topics, like always, like we do in our show. In particular, tonight we want to discuss the idea of different type of regressions, right? Because we will go a little bit in depth about that. But usually the idea is that you can see, if you take a log graph, you can see that the data becomes linearized, right? It's striking how orderly became the price of Bitcoin becomes, right? There are oscillations due to the bubbles, but in general, you see that it follows a very precise linear path, like what it looks like a straight line in general. But the idea is, well, how do you represent that, right? What is the best way to represent this linearization of the data? And there are different approaches. Some have some limitations and advantages, like in everything you do. And we will discuss these mostly tonight. But Stephen wanted to say something else about some other calculations that he did, right? You go ahead,
Yes.
Stephen, please.
Okay. Happy New Year. Good to be on with you again, Giovanni. And let me just go straight into sharing the slides. I think you might have to give me permission because, let's see, allow to share.
Yeah, put the slides and I will activate them. Is how usually we do it. Yeah.
Are you seeing it?
Yes, okay. We see your screen with the infinite talking about regression.
Yeah, we got. Let me try just playing this. You see it now, the slide?
No, it looks black.
Oh.
So sometimes instead of sharing screen, it says presentation, maybe. I don't know. Or maybe you have to.
Yeah, I asked for it to share the window, but let's see. Allow to share screen.
Screen, yes. Okay. Yeah, but now we see it. Perfect.
Now you see it. Okay, good. Great.
If I can find a format that is good.
How's that?
Maybe this one. Yeah, perfect. It looks great.
Okay, I just have a few slides to show today. And actually, what we're going to talk about is quantile regression with corrections for autocorrelation. And, the long-term view, the whole point of these regressions in log space is really to give you a very big picture view. And we've seen that the power law has been adhered to now, for 16 years that Bitcoin has been existing, 16 years in a week, we're happy to say. But just to also give you some other broad context that comes from a little bit different spot, I wanted to show you this Fidelity chart that just popped up yesterday.
Wow.
Some people will have seen a different Fidelity chart that's equally as impressive or almost as impressive. And what this is Fidelity is just rank ordering 22 different categories of investments. So if you look down here, and they're all color-coded, they have things like the S&P, which is SPX, they have REITs, they have Europe, they have Japan, they have gold, they have, commodity trading advisors, on and on, long-term bonds. So it doesn't matter too much for our purposes exactly what all of these are. But in the other chart that probably a number of people have seen, it showed that Bitcoin was number one in 11 out of 14 years. And then in the 3 years that it was not number one of all 22 categories, it was dead last. So this we understand about Bitcoin is that it's highly volatile.
And Bitcoin is like orange.
Bitcoin is orange, and it's at the top of the chart.
The be. Okay, yeah.
With our special,
from 15. It's a little weird because why Bitcoin will not be better than anything in 2009, because 2009 did like 2 or 3 times in a year.
Giovanni, this is a 5-year return.
Oh, okay.
So it only starts in 2014. So it's taking the 5-year history. It's the 5-year average compound annual growth rate.
Yeah.
2015,
average over 5 years. Average over 5 years. Okay. Because
so
otherwise, Bitcoin would have blown out of the water everybody. In that 2009, it was like 2 or 3 times or something.
Yes.
Okay. Yes.
So basically, Bitcoin, if you take a 5-year window, a sliding 5-year window, for the past 10 years, Bitcoin won 9 out of 10. It won every single time except for 2022.
Right.
For the 5-year window. And even for 2022, it was still in the middle of the pack. It wasn't at the bottom because, again, it was a 5-year window. So the message is buy it and hold it for 5 years, right? Don't just hold it for 1 year.
Yeah.
That's
actually a little unfair for Bitcoin because of the cycles, and the cycles are 4 years. So if you get the cycle, the 5 years at the bottom, right, you're including that entire year of losses. And this is why I probably did bad in 21, because that was the bottom, right? Of
2022 was a down year, obviously.
Right. And so, otherwise, and LG, what is LG?
LG is large growth. So the number 2 category has been, the big obvious growth stocks like the Magnificent Seven.
Yeah. Okay. Yeah, exactly. Yeah. And I think it was I don't know. Do you know the exact values? Because I bet Bitcoin was not far off, because even in its bad years, like if you average it over 5 years, you should still get pretty good. It's interesting.
Yeah. Well, we know that it was running above 50% if we go back, a couple of years, right?
Yes, absolutely.
Under the power law, you were always above 50% as your mean return. So So that's just a little bit of context for everybody. Now that we're below $100,000, don't get too worried. Okay, absolutely. So on to quantile regression. So you may have seen other quantile regression charts before. This one uses weekly data. So it's got all the weekly data up through the middle of December. It's over 750 data points. It starts early in 2010. So it's more than 15 years of weekly data. And you see, in the light blue, the bouncy numbers, which are the prices. And of course, this is a log chart. So what we have is the log 10 of price on the y-axis going from less than 10 cents up to, $100,000, where the log 10 would be 5, right? And then we have the age. Log 10 of 0.2 is about 1.6. So it's a little over a year old, a year and a half. Going up to, log 10 of age 1.0 is 10 years, and now we're at 16 years. Now, what a quantile regression does is it basically draws the line such that, there are that many percentage data points above that value. So and it's actually the inverse of that. So let's explain it. So if you take the very bottom, the blue line, that's quantile 0.05. That means that 5% of the values are below that line. The next one is orange. It's right on top of it. Quantile 0.1, 10% of the values are below that line. And then 0.25 for the green line. And then 0.5 is the median line. If you do an ordinary linear regression, you'll get the mean. This is the median. It's slightly different, but it's basically the core trend. So one thing that's very interesting to observe here is how bunched up all these lines are at 0.1, 0.05, 0.25, right? They're sort of all together, and they're providing a very firm support and foundation
Absolutely.
for Bitcoin's long-term power law.
So when we do the quantile, right, you're basically taking all the data below your reference, let's say 1% or whatever it is, or 5%, where the support is, and you're not throwing away all the other data, right? You're giving less weight. Is that how it works, right?
Right.
You are giving a weight that is basically 1 minus the quantile to the data you're analyzing, and the other one. So, for example, you will give 5% to everything is above 5%, right? You will give a weight of 5%, and you will give a weight of 95 to anything that is below the 5% quantile. Is this how it works?
Something like that. Basically, it's the optimized path through the data that puts 95% of the value above the line and 5% below. And you could imagine you change the slope a little bit, right? And you could still get 5%, but it has to be optimally weighted. Now, if we go up above, then we start
from an intuitive point of view, why the lines are a slightly different slope and they converge?
Yeah, exactly.
What is your intuition about that? Why do we have this?
Yeah, I was just getting to that. So if we go to the higher levels, which are the 0.75, 0.9, and 0.95 quantiles, then we're getting up into the bubble territory, right? So 0.95 is basically hitting the tops of the bubbles. They're just a very few data points above, 5% in this case. I mean, you could do a 0.99 quantile, but I'm not here to tell people you should focus on trying to nab that 1%. I'm saying, what are the long-term trends? And we're mostly interested where, the meat of the data is. And already 95%, is most of it. So the 75 to 95, those three lines are kind of up in the bubble territory, right? Kind of where the bubble starts and then near the top of where it finishes. Yeah. So what we see is, if you look in the lower right, you see the equations for all of these. And you see that the last number is the slope. It's the power law index. It's the steepness of the power law. So if you look for 0.05, 0.125, 0.5, they're all similar. They're all in this 5.8 to 5.9 range. So this is your fundamental support of your long-term
real power law.
It's
a real power law. Yeah, it's a real
what
power
you could call the real power law.
Yeah.
And then the other three, their indices are lower. They're less than 5.5. They're in the range of 5.0 to 5.4. Mm-hmm. So what they are reflecting is these bubble departures, which have this sort of exponential rise and exponential fall, up away from the power law and then back to the power law support. So you can think of roughly two domains. You could divide it at the meridian, which is 0.05, or you could divide it, higher at 0.67 or 0.75. I don't know exactly how you do it. Maybe you'll talk about that.
Yeah.
Later on.
Sure.
But we're basically seeing two domains. And the reason why these power law indices are smaller for these high-level quantiles is that the size of the bubbles in logarithmic price terms is decreasing. The volatility is going down as Bitcoin becomes larger and larger, and there's more capital inside the ecosystem. And so you see this compression, and that compression reflects the volatility coming down. If you do a standard OLS, ordinary least squares regression in log-log space, the overall standard deviation is about 0.31 in log terms. But if you look just the last 4 years, it's about 0.24. So it has steadily come down from over a factor of 2 multiplicatively to something like a factor of 5/3, about 1.7.
Right.
Now, the way this plot was generated was to first do a quantile regression and then to correct it for autocorrelation. And so what we're looking for is prices that are nearby that are correlated to each other. So you can do a lag 1, you can do a lag 2, you could do a lag 3. But what we found is if we
why would you want to correct for autocorrelation? Can you explain?
Well, what you're trying to do is basically there's momentum in the market, right? People trade, they see momentum, they hop on board. So it's just kind of human nature that you expect to see these things in financial series. And you can test whether you need that or not. So if you do the quantile regression, you test it with a Durbin-Watson statistic is what it's called. And you find out if you don't correct for the autocorrelation that your Durbin-Watson statistic is very close to zero. And what that means is that you have positive correlation between each two data points, that are 1 week apart, in this case, 1 week apart.
Right.
So what you can do is you take your regression and then you look at the residuals. And then from that, you estimate the correction for the autocorrelation, and you can take one or more terms. And what we found was that taking 2 terms was enough. If you take 2 terms, your Durbin-Watson statistics, this test for autocorrelation, comes out very close to 2, which is what you want. 0 means highly positively correlated, 4 means highly negatively correlated, and 2 means that you've eliminated the autocorrelation. And they came out very close to 2, like 2.0 this, 2.0 that. So then you redo the quantile regression with this correction method. And then this is the plot that's showed here. So it's a autocorrelation corrected to level 2 quantile regression. Now, first question is, where are we? And right now, the 50% median line is at $76,000. And the 75%, which is starting to get, up into a bubble, is 112,000. So, we're in a good place overall, even at 94 or whatever it is right now, 94,000. We're very much, and you can see that visually, we're very much in the domain of the power law, but somewhat in the upper levels. Any questions on this before I move?
No, it's very nice. Yeah, please.
Okay. So you have those 7 equations for these different quantile levels. And what you can do then is solve those equations for when you would reach different price points. And it depends on the quantile level. So if we go to the middle, the quantile 50, that would be the median trend. And you solve for when would you hit 300,000. And it would be year 2029.3. So, 1/3 of the way into 2029. And 1 million would be 2034. 3 million would be 2039. And 10 million would be 2046. And now those are on trend. If you're into a bubble situation, say you're at 90%, then it's going to happen sooner, right? You're hitting the 90% level, which is one of the upper lines on the prior chart. And so you'd be at 2027, basically, for 300K, just before 2032 for 1 million, 2037 for 3 million, 2045 for 10 million.
Mm-hmm.
So that particular number is kind of interesting because that's the Michael Saylor prediction, 10 million in 2045. Well, to do that, you'll have to be at the 90% level. So you can build this out for all the different quantile levels. And then you can also ask, what's the range of uncertainty for 50% of the probability space, which is the levels from 25 to 75, or 80%, which is the levels from the 10% quantile to the 90%.
Mm-hmm.
And you find that the width of, or the uncertainty is 2 to 4 years, basically.
Right.
So half the time, you'll be within a year plus or minus of what it's saying.
Mm-hmm.
So for $1 million,
it's amazing. Yeah, it's amazing.
yeah, for $1 million, there's a 50% chance it's going to be between 2033 and 2035.
Yeah.
Roughly. Centered on 2034.
Yeah.
All right. Now we can take these and, represent them more visually. And that's what I've done on this chart. Now here, what we do is we chart the probability of reaching a certain price by a certain year. in order to do that, we take 100% minus the quantile level, because it's easy to exceed the 5% quantile, but it's hard to exceed the 95%, right? Your chance of doing that is only 5%. So we have the year on the y-axis increasing, and on the x-axis, we have the percentage chance of reaching a level, but the numbers run backwards. So the way you would read this is, for 300K price point, I have a small chance of reaching it in 2026 or 2027, 10% or less.
Right.
But I have a very high probability, 90% or better, of reaching it by 2031, and the mean expectation is 2029. For $1 million, the chance of reaching it in 2025 is 0. I would say it's 0.01%, something like that. It's extremely low. It's like a 4 standard deviation outcome.
Yeah.
That you would have to happen in this year. More realistically, less than 5% chance by 2031, expectation by 2034, and a very high probability that you'd reach it by 2036. And then so on for the other two. 10 million. It's interesting, the curves become a little flatter. So 10 million, it's 2044 at the earliest. I mean, unless you get really lucky, and then it's 2049. You'd absolutely expect to reach it by then.
Yeah. Now we have to make a little exception to this. I need to figure out this. But what about? So this is considering. I think actually, in a way, the cycles are indirectly involved here, right?
Yes.
That's why. Yes.
Implicitly, but not explicitly.
No, explicitly. Yes. Yeah. This is why you get lower probabilities until basically you reach the year where you will expect that peak to be, more or less, right?
Right. So if this, for example, let's go back to the table. Now, our peak years were 2017 and 2021, 2013 before that. And so we expect this to be a peak year, 2025. We also expect 2029 then would be a peak year, right?
Yeah.
And so the 300K, it says 50% by 2029, and then 75% 2028. Well, the chance of hitting, say, the 75% level in 2028 is higher than this table is implying, right? Because we'll already be well into the rise, and
yeah,
you won't be at 50% in 2029 if the quasi-periodic 4-year bubbles repeat more or less in the same pattern.
Mm-hmm.
And so you'd expect it to happen maybe a year sooner. And it's possible that it could even be 2 years sooner. But, to get to the 90% level, that's 2.4 years, and that's a down year, right? 2026 is going to be a down year.
Right.
So the chance of hitting it in 2026 is probably not too good.
Yeah.
So this does not explicitly take account of the bubble peak years. It also does not explicitly take account of the troughs in the winter years.
Correct. Yes. But it's still a good reference. I like it. I love it. I love this chart. It's very nice. Very good. Very well done. Yeah.
Okay. Well, that's what I had today. So.
Yeah. Okay. Very good. So, and on my side, let me share the screen. So let me see what where is okay, here. Yeah, so this is about elaborating on this idea of a quantile model, right? So basically, it's a discussion that I had in the last few days. Maybe you follow it. Actually, you did follow it because you replied to one of my posts, and this was mostly a conversation that I had with Plan C, because Plan C is one of the people that are working on the power law that likes that model a lot. And I think there are advantages and disadvantages, and I can tell you what I think some of the advantages are, some of the disadvantages. You work with it, you actually improved on it with using this autocorrelated corrected version of a quantile. But here I'm showing, and without going too much in the formula, but basically, and you can correct me or add to what I'm saying in general, right? So the way this works is this. And sorry if I maybe go a little bit in a long explanation, but the idea is, right, we start with the power law, right? The power law, imagine you don't see the lines here at all, right? You just see the price and you plot it in a log chart. What I was saying before, it looks like a straight line. What do we mean, right? Because maybe it's clear for me and Stephen, because we have played with power laws all our lives, because they show up in physics all the time. And to us, this immediately, I see something like this, I say, oh, it's a power law, right? Because it looks to me straight. I don't care so much that it is oscillating back and forth. I look at the general trend. So I will not need even a straight line to tell me that. I will say the data is linearized. And by the way, it's not easy to see this kind of behavior at all. Now, I didn't see many power laws. I don't know you, Stephen, that are oscillating like that. It's not. It's almost like there are two signals, right? There is a general power law trend, and then there is this sinusoidal signal that is on top, right?
I have a physics analogy.
Yeah, go ahead.
The physics analogy is from fluid flow.
Yes.
And sometimes your flow is laminar and sometimes it's turbulent.
Okay.
And you know, the peaks are sort of turbulent, chaotic flow that, right, on top of that emerge from laminar flow underneath.
Right.
And so it's like, you know, you think about the ocean, the waves, right, on the surface are chaotic.
Yeah.
And it depends on the depth of your lake or your river, you know, how chaotic the surface can be relative to the total volume of the flow.
Very good. Yeah, I want to study more of that example. But yeah, it could, you know, it could be a situation like that. My way of thinking about this, I don't know if you agree, is almost like there are two signals. Now, they could be related because there is a lot of work on how, in particular, you know, in the log periodic power law, how actually bubbles emerge from, you know, behavior that it's power law like, because power law many times are associated with phase transitions. And then at the phase transition, you start to see these bubbles, right? It are basically deviations from these from the behavior that you had before. So it's possible that they're actually kind of related to each other. But right now, from a signal point of view, you can think there are two main signals. There is the general trend, that is the power law, plus there are these, they are not really sine waves, but you will call them quasi-periodic or, you know, sinusoidal oscillations. Now they do look like they are becoming, you know, the distance is smaller, but this is an artifact of drawing them in this, you know, log graph. They are actually equally distant at about 4 years. Now, the first bubble is a kind of anomaly because it didn't. The distance is more like 2 years from the next one. And we don't know how to explain very well. Well, in general, we don't know all the details of how bubbles are created, but even less the first one, right? It seems that it doesn't follow the pattern of the other three. Now, what you see many times when you you find power laws in nature is more something like this, where there is a bunch of data this is actually, by the way, the relationship between the price of MicroStrategy and Bitcoin. The data is all over the place. It's kind of noisy, right? It doesn't follow a precise pattern. There is not a second signal on top of it. It's just that there's some kind of relationship between the two, maybe a power law, like this graph shows. But I'm showing mostly this to tell that, you know, it's unusual to see a second signal right? And anyway, the idea is, we draw these lines. What these lines are supposed to represent, right? Why do we draw this line? Our intention is to say, look, forget about the oscillation. They are there, but in a sense, because some oscillate, like if you thought about this like a straight line, like there was literally a straight line through the data, right? Because when you do this mathematical thing, there is always you need to focus on what we are trying to tell us, right? And what is the interpretation. So I'm drawing a line, and then that line is supposed to represent the general behavior. This is where the modeling part of a model comes, that you are saying, these ups and downs are not the main message here. The main message is that we are going up in a straight line in a log graph. It's actually a more complicated relationship than a straight line. It's a power, right? We discussed this many times. Is y equal x to some power. In this case, some number close to 6, 5, something. But let's simplify it to 6, right? So that straight lines, it means there is some kind of a simple equation that is kind of a dream of physicists to find simple equation that describe a world, and it can be identified by drawing this line. Now, we don't draw these lines by hand. We use mathematical methods that they have very precise meaning. There is some logic behind, right? We are trying to do certain things, and the goal when you're trying to find these lines is to find two things, because lines are defined by two numbers: the slope of a line and the y-intercept, where the line is intercepting the y-axis. If you know these two things, then you can identify a unique line, and this is all what you need, these two numbers. So when we do these regression methods, basically this is what we are trying to do. We are trying to find these two numbers, right? This is, you can recognize this probably is from ChatGPT, but basically we are looking for this beta 0 and beta 1. Beta 1 is the slope. You see, this is the general shape of a straight line. You have a constant and you have a slope, and this is our model. This is what you will say, this is my model. I have this model in mind that basically I'm dealing with a straight line. And it's a simplification. Of course, it's a simplification, right? Like the other day, somebody was saying, if you are talking about oscillation around a straight line, it's not a straight line anymore. It's still a straight line, because if I have oscillation around a trend, the oscillation kind of cancel each other, right? If you are above, there is an equal amount of data above the straight line, and below, they are going to cancel each other. So I can still say, in a mathematical and logical meaningful way, that the data can be simplified and represented by a straight line. And this is my model, right? And there is, of course, you lose something when you are simplified, and you gain something. You gain simplicity. You gain like a general idea of what the price is going to be over a long period of time. And what the normal type of regression does is simply try to minimize the distance. So because we are trying to do the physics of Bitcoin, so we go a little bit more in details than we will do otherwise in other Bitcoin shows. And hopefully we are still having people following us. But basically, what do you do, right? This yi, is the price, right? So imagine I go through all the data points. That is basically, usually we do it with daily data. You could do it with hourly, monthly, anything, but most of the time we do it when Steph and I and other people do it, we use daily data. So these are the daily data, the prices every single day, and you go through these sum. You see this symbol here means a sum. So I'm summing all these differences. What you're seeing here, this is the difference. Is the difference between the theoretical value, that is my model, and the real price, the real price at any given time. Remember, this theoretical model, it's a kind of right now it's an abstraction, because we don't know yet what this beta 0 and beta 1 is. We are trying to find it. And how do we
Giovanni,
find it? Yeah.
So just to shorthand that basically is minimizing the sum of the error squared. So it looks
Error
at the
squared.
error or the residual at any data point between the model and the price. And then that's the error. And then it squares that and it sums them all. And it's trying to minimize that sum
minimize
over the
that. Right,
whole
exactly.
set of data.
Yeah, so Stefan explained it faster and better than me. So I'm looking at the difference here that are basically the error. So how far away your real data is from the model, right? Because if I measure the difference, that will be the error. And then I square it. And why I square it? I square it because I don't care if error is positive or negative, right? Some of them are going to be above the power law, some of them are going to be below the power law. I'm just looking at how big the difference is, independently of a sign. And then I sum them together to give me the total error. In a sense, it's like an average, when you sum them together like that. And then see, it says here, find the minimum, right? All what this means is, let's calculate how big your data points, right? How big the error is. So basically the distance, the difference between the value of a price versus your model. And let's find the beta 0 and beta 1 where this sum is minimized. It's the smallest possible value that they get. And you can do it in different way. In theory, you could loop through all the possible values, right, in a range between, this value to these values that seem reasonable until, you get all these values, all these errors, and then you choose the smallest one. Actually, it turns out that this can be solved with calculus. There is a classical solution in calculus that actually finds the solution for this problem. Okay, this is the advantage, for example, of least square regression. That is something that there is an equation to solve that. So it's a relatively quick method. It's also quite simple to understand in how it works, right? When you do more sophisticated things, the problem many times is you don't know what the algo is really doing, right? Maybe it's doing the correct things, but it's a more complicated of a process. Here, it's a very straightforward idea. And this is the simple regression, the classical one that most of us show when we are talking about the power law. This is what it does. The quantile one is this process, right? And it's a little bit more complicated, but also it's supposed to be more robust to large deviations, right? So if there are large deviations, like in this case, for example, we have a bubble, so to deal with, this method actually is supposed to deal with that better. What it does, basically, again, the goal is the same, because you see this quantity here, y hat, this, how we call it, a lot of physics and mathematics is all about understanding the notation. Many people get stuck because they get lost with the notation. But all what it means here is simply this model. So again, we have a model that looks like a straight line, and the goal is to find beta 0 and beta 1. And we are measuring, in this case, we don't measure the square of errors, but we measure the absolute value. It's a slight difference, not big. But again, the difference, right? The error. And the main concept, you see this Q here, we are giving different weights to the data. So the data that is below and above a quantile. If it is below a quantile, like in this case, for example, right, we give, in this case is above, right? You see the data points are above your model, and the model is supposed to represent the data at that quantile level. So let's say 10%. So if it is 10%, 10% is 0, 1, right? If you express it as a ratio. So you're giving a small value to all the data that is above a quantile, in this case, 0.1. And if you subtract 0.1 from 1, you get 0.9, that is 90%. So you're going to give a huge weight to all the data that is below the quantile. And this is how you do it. And you do it for different quantile. Like, for example, Stephen was showing, what did you show? 5% quantile?
5, 10, 25, 50, 75, 90, and 95.
Exactly. So you will have different lines, right? And the goal is the same. This is a loss. So you're trying to minimize this quantity. To make
so two things here.
Yeah. Go ahead.
One difference between this and least squares is that this weights the errors linearly. So it takes the absolute value and it weights that linearly instead of the square. So the outliers don't get heavily weighted as they do in least squares.
Okay, very good.
So that's one advantage. And then the other, of course, is what Giovanni just described, which is it's trying to find, 95% of the points to be below the line and 5% above. So it weights them by that level. If you took Q to be 0.5, this thing would collapse, right, into just summing up overall the absolute values of the errors. It would just be a sum over the error absolute values. And you would minimize that as what we call the loss function. So there are two basic differences, but this one ends up giving you an array of lines instead of a single line. If you
why in general people use the square then? Why will you not take the square root of that, like you will do with standard deviation? Why they stick to the square? Why?
You mean in least squares regression?
In least square regression, because will you not be always better at just taking the absolute value instead of a square?
Linear absolute value regression.
Yeah.
Does that admit of an analytical solution?
Maybe not. Maybe that is the problem. Yeah. Maybe there is
I think it comes from actually the assumption of Gaussian statistics or log normal statistics. Correct. So if you do it this way, and if you have a Gaussian distribution, and then you pull out from here a standard deviation as well as a mean, right? So it's kind of from that world of normal Gaussian statistics and log normal statistics, which we don't have. We don't have. Exactly. We have a highly skewed distribution.
Correct. Yeah. I mean, it's amazing that it still works pretty well, because if you really compare, you superimpose, and I can show in a moment, superimpose the 50 percentile, the quantile, with the least square, they are very similar. They are not that huge of a difference. Still amazing. And the main reason is because of this, like something that we have noticed so many times, this thing, where really, even if these are very non-linear events, right, when we leave a power law and then we come back to it, right, it's really, is why the quantile is a more appropriate approach. They kind of cancel each other. You leave a power law and then you go back to the power law. It's really almost shocking that how this happens so regularly, right? We leave a power law and then we go back to it. We leave a power law and then we go back to it. So they kind of
almost not show the skew, though, because we have that heavy skew such that we rarely drop below -1 standard deviation, but we can often go above 1 into 2 standard deviation on the plus side.
Yeah. And so, in general, yes, this method is supposed to be better. The problem is, my main issue with Plan C, it's a matter of interpretation, right? Because he push it in a direction that I don't think is the correct direction in terms of interpretation. We can discuss that in a second. So his interpretation is this, right? So he shows this model that is his quantile realization that is similar to what Stefan just showed us. And his argument is this, and I want to discuss this argument because he has a lot of followers and he's trying to say these things, and I disagree. It's not that I'm trying to criticize him. We are having intellectual, logical discussion. His idea is, well, now that I have these probability bands, right, and these probability bands can be drawn anywhere. They are not localized to a particular region. They continue at any place. It's not just that now. Before, when we had only the main regression, we could have done that too, and we have done it often, right? We draw a support line, we draw deviation 10%, 20%, but it's difficult to give meaning to these deviations, right? The support seems to be meaningful, the other deviations not so much. But now we are talking about probability, and so his idea is, well, basically, at any particular point, imagine I am here at the bottom, right? Like last bottom with we were $16,000. Well, there is a chance that the price can be anywhere in these bands. And if you take a face value, the quantile approach, right, where you have all these probability ranges, yes, that is true. There is like a non-zero chance, and maybe you could, I don't know which one they drew, but imagine we're using.
There's no chance whatsoever. You don't
right.
get quantum transitions by an order of magnitude. Right?
Exactly, right? Exactly. So it will, you have to be careful between what the math says and many times, in physics, many times we see some mathematical solutions and we say, oh, I'm not going to ignore this mathematical solution. Like, for example, you're getting a negative sign where you should get a positive sign. You get maybe the solution of this equation is both negative and positive. Mathematically, yes, but physically cannot be, because you cannot have a negative mass, let's say. I'm just making an example. Or if there is a solution that is negative mass, sometimes some crazy physicists will take it seriously. Oh, maybe that means something, right? And usually, it is a breakthrough that changes physics forever, because you're interpreting, you're thinking that there is this thing that seems crazy, and then it really comes out to be real. Or most of the time, it's just like you're using mathematics, and you have to also look at the physical meaning of what you're calculating, right? Is that
you cannot just look at this and say, what's the chance of being in a band? You also have to look at the slope of the price increase at any given time.
Yes.
And what is the distribution of the rate of the price increase in the bubbles, which are exponential and sometimes supra exponential.
Exactly.
But still, you have to look at the full distribution of the rate of the price increases. So if you had that, and then you look at the, last data point, then you could use that for a probabilistic projection as to how fast you could climb, right?
Exactly.
And that would still be overly optimistic, because we only know you can climb that fast if you're in one of these quasi-periodic Fourier space bubbles.
Yes. So, is interpretation, but now that we have this model, we can get rid of the cycles. We don't have to basically, he would like to take it where, like I just say, if we are here 16,000, and you go to the highest value, whatever that is, maybe it's like a 90% quantile or whatever, and that 90 quantile, basically we say, well, there is a 10% chance that the price is above there. No, it's zero, like Stefan said, because first of all, imagine if you take it really literally, it means you mean tomorrow, that tomorrow we could, by chance jump to 200,000. I remember I did it. It was like something close to whatever, a big, huge value, 200,000 or something like that. So are you saying that it could go all the way to $200,000? No, it's ridiculous. It's not. Maybe what? No, I think it was 80,000 or something like that. I don't remember, but some huge value, right? You are at 16,000, and this model says, well, there is a 10% chance that we go to 80,000. It doesn't make any sense. It's not how to interpret. So it's very important when we do these models to stop and trying to understand what they are saying, what is the interpretation. So it's not true that is, he called it a time agnostic model. It's not, because you will force an interpretation that is not really what this model says. And maybe Stefan, you can help me. My way of thinking about this is you still have to be cognizant of the cycles. And when we are in the proper region, like for example, when we are close to a bubble, then it will tell us, okay, usually the bubbles are these large deviations. We are actually in bubble territory when we have really large deviations. And the likelihood that we go even higher than that, it becomes smaller and smaller and smaller. So in a certain sense, they give us a ceiling, but the ceiling needs to be applied at the right time until this picture continues. Now, if we have in the future, we will have a situation where we don't have bubbles anymore, where we only follow, let's say, the power law, and we have just maybe small deviations around the power law, then it's different. Now you will take that statistics and you will create a completely different model. It's still a power law model, but it will not have these very large bands that try to include all the different behavior of Bitcoin. Do you agree with that picture?
Yes, I would say, look, right now, if you say, well, we're roughly around the median level, you can go back and look at the prior 2 or 3 bubbles and say, well, what's the most rapid rise you had? And that, gives you a general limit as to how fast you could rise from here.
Exactly.
Yeah, it could be still quite steep. I mean, we could go a factor of 2 easily in 6 months, right? We're not disallowing that. But we're saying it's not going to happen tomorrow. So it is state dependent as to where you are, how fast you can get somewhere else.
Right, exactly.
And this tells you what the maximal somewhere else would be. It doesn't tell you when. And the statement I just made has nothing to do with when the bubbles occur, right? It's just we already know how fast bubbles can rise.
Exactly.
And we even have, you have a whole framework that derives from Sornet's modeling around bubbles.
Exactly.
And I've even played with that a bit, these log periodic power law.
Yeah.
Bubbles that, you can observe those and you see how they rise and you see what their time scales are like. They can be measured.
Yes. And another thing I did was this graph. So basically, I was interested in understanding how these deviations from the power law look like. Now, when you talk about deviation, you can do it in different ways. For example, when we saw that equations, these are differences where price from the model versus price, the real price. But, if you want to compare them on a global scale, you have to normalize them by something, right? Because one thing is to take the difference between 50,000 and, let's say, the model say 50,000 and the price is, 53,000. And the other is when Bitcoin was $20, right? $20 versus $5 that the models predicted, let's say. So it would not be easy to compare. The way to compare is to express them in some kind of a percent. So, for example, you could take the difference between price and the model and then divide it by the model, right? In that case, it's going to be some kind, it's called a percent difference. So if you look at this percent difference, so price minus trend over trend multiplied by 100, then it looks like this, right? And what did I do here? Because basically I kind of played plan C game. I say, can we pretend that there are no cycles? So they are scrambled, right? They basically can happen at any time. Any deviation can happen at any time. And so I scramble the time. I scramble the order, not to be distracted by the oscillation. Because if I didn't do that, and then I will see some kind of behavior in time. I wanted to erase that behavior in time by scrambling. Do you follow what I'm doing?
Yes.
Yeah.
You randomize the times. Okay.
And randomize the time, and you still see that it's not, a cloud. There is a real separation in terms of, you will say, and we are used to look at things like that in physics. There are two regimes. There are two states, right? There is this state and there is this state. And I was very surprised on how narrow the range. Now I'm taking the log, right? So I took the signed log, so that helps a little bit. But still, you see how clustered the values are. So in this regime, when we are below the power law, because these are all negative deviation relatively to the power law, we are very, very clustered. So when people say that the power law is not very precise, they don't know what they're talking about. Most of the time, when we are below the power law, we stay close to that support line, and the support line is kind of there. And you see, they are clustered around there. Yeah, it's now quite interesting result.
That is interesting. There are definitely two regimes here. I could ask a clarifying question. So you're saying 54% of the data departs by at least 10% in the negative direction, right?
Correct.
And 38% of the data is upward by at least 10%.
Correct.
And only 8% of the data is within the plus or minus 10%.
Yeah. And the power law is here at 0. Maybe I should draw also that, where we almost never there. So in a sense, is representing the behavior, the 50%, the middle line. At the same time, we almost don't spend any time there. It's a transition region, It's really cool.
The red and purple lines, what are those?
It's one standard deviation away. So if I remember well, yes.
Oh yeah, yeah. Okay.
Yeah.
And what's the purple line? Is that?
So 1 and 2 standard deviation. Yes.
It's 2 standards. So that's 1 and 2 standard deviations.
Okay. Yes. And from these regions,
Yeah.
and so that really made me curious. And the other thing I improved on this by saying, what if I actually normalize now by volatility? And when you normalize by volatility, now it's even more clear that you have 2 regions. You have 2 modes, and they are very similar. So I think this shows.
I'll be right back, Gio.
Yes. I think this shows that actually all what we are seeing, this behavior of a bubble, right? The fact that we have these huge big bubbles is nothing else than additional volatility. Because the reason why we had this huge big bubble in the beginning is because there was more volatility. So in a certain sense, we are saying the bubble are nothing else than power law behavior that is above the general trend, because we are in this regime where the daily returns are higher than the normal power law, plus additional volatility. When you take the volatility away, then in the entire history of Bitcoin, basically the bubble behaved in the same way. It's nothing else. In fact, it doesn't look very different from this. It's just that now you are a little bit above. Instead of being below the power law, you are above the power law. But it's basically the same behavior. So it's kind of 2 modes where Bitcoin is, and it's doing power law things plus volatility. So the bubbles are nothing else than power law plus a bunch of volatility that you don't have when we are not in a power law. It's a really, really cool result if my interpretation is correct. And I will, maybe I can repeat this when Stephen returned. Probably had to go to take care of his kids or something. But yes, I don't know if you guys have some questions about. But it basically is a really cool result. And now, I put this together, and I was trying to say, is there a way? And it's a work in progress. I think we can still use this information that we have really this corrected deviation, like this here. For example, Stephen corrected the quantile model, with the autocorrelation. I'm correcting this using volatility. So let me repeat, because I would like your feedback on this. So in this case, what I did, I took the same picture than before, but now I corrected the data, the deviations. Instead of dividing by the trend, I'm dividing it by the volatility. So the standard deviation of the returns over, I think I use 120 days window, something like that. And what I'm seeing, and you tell me if you agree or not in this interpretation, is that the 2 regimes are very similar in the sense that if you really want to explain the bubble, once you include volatility, so basically correct for a volatility, you see this uniform, very consistent uniform behavior across all the different times of existence of Bitcoin. So one interpretation is that the bubbles are nothing else than you're moving along the power law still, right? If the signal is still there, but now you have this additional volatility. And that explains both why we have a bubble, why we have this huge big deviation from the trend, but also why over time they decrease. Because if a volatility just decreases simply because of this how power law behaves, right? We have diminishing returns, and so you will expect also the standard deviation of the returns is decreasing. Then this is why the bubbles are smaller and smaller. And this is it. It's a really coherent picture of how Bitcoin behaves. You kind of agree on this interpretation?
It certainly looks like a mirror image. I think so. I want to hear more about it and try to understand it better, but it seems
Yeah,
reasonable.
it's worthwhile to explore
Yeah.
it, and maybe you can help me.
Yeah.
And this, I just lost it. And this is the distribution. This is how the distribution looks like, for the
Yeah.
two regimes. That it's clearly bimodal. There is no, if anything, you could say maybe this is more like an exponential distribution, and this maybe is Laplace distribution, and basically say here is the most likely value. Again, notice 10% away from the middle, and this is where we spend most of our time, and then there is some chance to go away all the way to 40%. But this 40% not from here, but actually from the from this value here, right? So actually it's 30% from this value. So it's much more narrow relatively to what you were going to say if you just relied on the least square approach. And I try to put all this together in an indicator, and this, it's a work in progress, so I'm still working on it. I'm going to share in a moment to show you how it looks like when you actually make an indicator out of this. I'm going to share my screen. Okay, this one. So it looks like this. So, and like I say, I'm still working on it. But basically, you see there are two regimes. So what I'm doing here, I'm taking only the data. Maybe there is a better way of doing. Maybe using Quantile will be better. Using the 50%. So, or the median. One could take also the median. But right now I'm using the standard least square, and then I'm using it as my as a reference to cut the two regions. So I'm saying the code works where it's looking for all the data that is only below the power law and only the data above the power law. And then I'm calculating the stats. I'm calculating the average. I'm calculating the standard deviation, etc. And I'm making these basically kind of what you were saying, because here is the volatility that represents how fast we are moving away, right? And it's color coded where the value of the volatility is represented by different shades of red or green. And the dark line, it's the average behavior. So the average behavior during when we are below the power law is this dark line here, and when we are above here. And now you can see that the bubble are nothing else than just basically the darkest regions are two standard deviations. Are two standard deviation from the mean. And mean here is not the blue line, that is the general average. It's the relative average for that region, like the region above or below the power law.
So
this is how it looks like. It's
really
cool,
nice
right?
visualization. Yeah.
Yeah.
Those standard deviations, are you calculating volatility over a 120-day window, or what's?
Yeah, it's actually the algorithm allows you to choose whatever range
but
you
something
like
that, huh? Yeah.
Yeah, in this particular instance, this is what I'm using, but you can choose it. It's actually a variable that you can choose it. So right now I'm choosing 120 days, but you can make it bigger, or if you make it bigger, it becomes more consistent. If you make it shorter, let's say it goes to 60, it's more sensitive to local changes, right? You see. But I think 120 is a good compromise. But one can play around with different values, etc. This is a usefulness of indicator. By the way, I'm going to send you this indicator so you can actually. I'm going to send you an invite for the indicator so you can play with it and you can tell me what you think. But what do you think about this approach? Do you have any feedback? Do you think it's an interesting way?
Wow, I like it. I mean, I certainly like the general, proof. The word's not proof, but the word is demonstration that we have two regimes going on here, right? And I think you've clearly demonstrated that. And this visualization supports that, but I think this is a nice, compelling way to actually show it, for practical purposes.
Exactly. And basically, so if you want to talk about what is going on with the power law, you really have until now, until we have some evidence that the cycles are not repeating anymore, etc. But at this particular point, you really have to be aware of where we are in the cycle, because if we are above the power law, we have a different type of statistics. There is a different mean that is very relevant right now. It is interesting because I remember you say that your 75 percentile was about 112. I was pay attention when you were saying that.
Yes.
And in my case, is 117. That is the average. So maybe it's the 70 quantile, right? That is a relevant value when we are above the power law. That is your point of reference, where most of the data happens, right? That is where that concentration, that clustering was happening. Most of the deviations, if they are expressed in that way as deviation that are quantized, that are normalized by volatility, then this is where they are supposed to be. And you can see it's really almost like there are two power laws. There is this power law and there is this power law, right? And we switch between one and the other. And now the bubbles are nothing else. Like basically, I'm not sure I'm doing yet what you were explaining before, but I like it. If you have an idea of what is the current volatility, and you add that volatility, because remember this, it's adaptive, right? It doesn't know. I like TradingView because it doesn't allow you to cheat. It only use data up to that point, right? So right now I'm drawing these contours based on the recent volatility, and it's telling you, look, imagine you wanted to know where we can go, how farther we can go. You will say, well, usually when we have the top of the bubble, we are in this region, which is the darkest one, right? You go 2 standard deviation away, and it's telling you where it is, moment by moment, is there, So unless I'm misinterpreting what is happening here, it's basically kind of almost predictive of what is the possible range, and it kind of adapts because it is given the volatility is less here, it's still doing a good job in telling us what is the range of possible values.
It's a little hard to see, so I might do something to the shading for that last contour.
Okay, and I will send it to you so you can play with it. Yeah. But here you can see the shading really kind of follows, the real price action, and it's kind of telling us, they basically, given the current recent volatility, these are expected values for the top, right, at any particular time. And what I really liked is the fact that for all the different bubbles, because it's basically correcting for the volatility. As we go back in the past, it allows for larger volatility, right? And so it's really cool, in a way, if my interpretation is correct, is it's kind of expected with this volatility that is typical of a bubble for the price to go here. Not much further, because if it goes much further, right, it's beyond what is the usual statistics. But given it's about 2 times, usually no more than 2 standard deviations, this is where you will expect the tops. I do you think it's the right interpretation? Or am I explaining it correctly?
It feels right. For me, what's really kind of compelling is how regular the phase transitions are.
Right.
That you don't get a lot of fake outs. We have one little bit of a fake out, in the middle of the chart with a short green and a short red zone.
Exactly.
But other than
notice
that,
what happened. We had a correction, right? So
yes.
Right, and maybe we can find out what happened there. Maybe it was some kind of bullish event or something that pushed the price up. But then he said, well, I should not be there. It's better for me to go back where I'm supposed to be, right?
Yeah,
and it's really cool.
That was before COVID. Let's see. Okay, and there's COVID. I find that very interesting. It transitions to one regime and it stays there for quite some time.
Yeah, and the same thing here, right? This was the ETFs, and actually it was kind of cool because we touched the power law, and then it needed to correct, right? It was too much. So the interpretation when you are below the power law will be, if you have too much of a deviation from this trend where the clustering happens, right? The clustering of the data happens. That correction, that data will correct itself, right? For example, one way of thinking about the bottom is that you are too much far away from where you are supposed to be, and so it will not last. It will have to correct upwards, right? Because it needs to go back above to this region. And the same thing here. We were too far away from the power law, in this case, too bullish, and so the price needed to correct. That is exactly what happened, And then there are these very, very sharp transition. Notice how fast we go up, right? We don't spend much time in a long way transition. It happens relatively quickly. And it's something that, I don't characterize right now. Maybe there is a way of characterizing, maybe color coding, give them yellow or something, but and see what they look like. It's not many data points, so it's difficult to do stats, but it's clear to me there are two regions and they need to be treated separately, right? And then when you do that, when the power law gets a new understanding, and because one of the things that many people criticize, right? They say, are you telling me that the power law can go anything from here, the support line, all the way, to 2 standard deviation above or 3 standard deviations above the blue line, right? It's still confined. It's not like, oh, tomorrow is going to be $1 million, right? It still tells you something. That is one of the things that I never liked about, because my intuition told me that is not what the power law says. It's still very aware that we have cycles, so you have to be careful about what they're discussing. So now I have a better representation of that really there are 2 power laws. There is a power law for winter and a power law for summer, and you have to switch to the right one when you are discussing what is going on with Bitcoin, So I quite like this model.
Yeah, I do too. I look forward to thinking more about it.
Yeah. Let's work together on it. Do we want to take some questions? We don't have today. We do have some questions. Let's see. So it's more like a comment. Let's see if you agree on this comment. You want to say something about this?
Yeah, I mean, I think that just says why people should examine whether there is autocorrelation, and if there is, you should correct for it. So,
and that you were also saying that when you calculate your R square, you get much better value, right? When you do the correction.
Well, it depends on the details. I mean, when I first did it, I did a generalized without auto. I did a generalized least squares without auto correction, and the R squares goes down. But the other statistics went up substantially. But for this one, the R squares are high. Yes.
And do you remember the value?
I don't remember the numbers, but they're sort of typical in the mid 90s. Yeah.
Good. Okay, and so there is this comment that says the Department of Justice just got approved to sell $4.5 billion. What do you think about it?
I think there's 11 more days for them to sell. After that, I don't think they'll be selling.
Okay, so that will be after.
I expect that sales will be halted after the new administration moves in, but we'll see. But
probably because of administrative reasons, they will not. It will pass much more than 10.
Okay, so the broader question is the one of the strategic Bitcoin reserve, and the way to jumpstart that is to stop the sales by the DOJ. So the Bitcoins are held by the Marshals Service, which is part of the DOJ, and so one could, by executive order, stop those sales, presumably. But in order to establish the strategic Bitcoin reserve, there will need to be approval by Congress. And there is a bill. Senator Loomis has put a bill in. I think people generally have heard about that. And the idea is to purchase 1 million Bitcoin over a 5-year period. Now, the
Right.
Bitcoin that's held by DOJ Marshal Service is around 200,000. So that could be a kickstart for the whole program. They would have to move it from DOJ into the Department of the Treasury. And that probably requires congressional approval as well. There's some debate as to whether that part could be done by executive action or whether that would be by congressional approval, but it would presumably be part of that same law that Senator Loomis has put forward. And but I think what can happen immediately would be halting any further sales.
I hope so. Yeah.
Yeah.
Bitcoin will recover. I think the power law is here to stay. In general, the main question is the idea of the cycles. That I still think they are a very important component of Bitcoin behavior, but it's something that we will have to see. And we have this other question about smaller time frames, right? So one of the things I noticed before, and there are different ways to answer that, but it's something that needs to be explored a little bit better. But in general, the power law tends to be valid also on relatively short time frames. Like, for example, notice how, if, for example, here what I did, I have all these lines that represent different deviations from the trend. By the way, this is a form of a power law that I call it adaptive, because basically it's taking all the data up to that point and then it fits with that data. And so it's a kind of a little bit sensitive to when you do the calculation close to a top or a bottom. It's mostly to show that even if you update the parameters on a continuous basis, you're still getting this general trend that looks like a power law. But one of the benefits is that I think it's a little bit more, able to track kind of local behavior. And so one of the things, and you notice, is it almost creates some kind of support and resistance levels. Like, for example, here, you see this was a support, and there are these very fast phase transitions. It's really curious. It really changes very much and then stabilizes again, and it goes and it follows the power law. Again, here, look, it follows the power law. There was a correction, and again, it followed the power law. Look at this. Here, look.
I don't think we can see your screen.
You don't?
No.
Okay, let me try again. I thought that you did. Oh, yeah. Sorry for that. Yes. Now you see it, right? So look at the top panel, right? This let me minimize the other ones. Sorry for that. Okay, so I'm talking about these, right? So you see how there are all these local power law trends. Like here, for example, this was it was clearly following, because it's parallel, right? The power law. And there is a phase transition, very fast change. It goes here, it stay there for a little while. Again, it corrects, it goes up and it follows the power law. It corrects, follows the power law. And then look at this. Again, here. So, if it happens one or two times, you will think it's basically a rise. But again, look at how it follows the power law here. And then it changes. If it finds it stabilizes along the power law here, because these are all different levels, but the trend is the same, right? The slope is the same. So really, to be the power law, it needs to do most of the time. Bitcoin needs to do power law things. It needs to kind of follow the power law. And now, for example, for some time we have been along this line, right? We have been like since November, basically. Sorry, since March, we kind of stayed along the power law, right? So yeah, it's kind of useful also to find these different. See, it's not something that happens just one time. It happens often, like here, right? It's almost like support, like mathematical. It's not somebody drawing in them by hand, but it finds this local power law behavior many different places. Almost creating some kind of support and resistance. So it's really interesting. Now, using the power law to make daily decisions, let's say you are a trader, selling at this moment and buying another. It's not something that the power law is designed for. You can include it, like for example, and one day we can discuss it. But I'm playing with some small portion of my assets, right? I'm using it as a collateral. I'm buying futures. I'm this algorithm that I'm working with another group is buying the dips and then sell when we are above, when we made some change, in our gains, when we sell, and we do this over and over again, and that's been working very well. One of the problems with these approaches is you want to avoid to be liquidated, and one of the things we are doing is to use the power law floor as our reference, because we know that we can create a bunch of orders where basically we are doing DCA down. It's called, the technical term is called a martingale. So you buy as you go down, you buy more and more, to kind of find a price that is as close as possible to the bottom, the local bottom. And your main risk is to be liquidated. So we are integrating the information that historically we never go below the support line. It's kind of a point of reference for us. So you can use the information from the power law to create a trading system, but I will not advise to use it as a tool to do daily trading. It's not designed for that. Beards looks like, my girlfriend wants me to trim it, and it looks too much like Santa Claus. So it was good for Christmas time, and I need some shaving. I'm actually going tomorrow to the barber because somebody's campy says that my beard looks great. Yes. Okay, so it has been fun. Do you have any concluding remarks, Stephen?
No, I think we're in a good place. We're set up for 2025, and we'll see how it unfolds. But we could get we're almost into that new regime, right? Or at the close to entering that new regime. Would you say? I mean, we're above the median, right?
Right. It looks like, right?
So
exactly.
We're in the early phases of it, and that's when things can move more quickly. Not a factor of 10 in a week, but can move quite quickly. So,
and this is why I would like to have the inauguration be happening, because I think I don't want to attribute to a person or a political event what happens with Bitcoin, because I think Bitcoin goes beyond these kind of things, but at least temporarily they can. It's almost like I was making the analogy. It's like when you have this critical phenomena, right? Like an avalanche. The avalanche is already there, and then if you go there and even just clap your hands, the little pressure from the air that you move can push the avalanche and make it happen. This is what happened with critical phenomena. You didn't create the avalanche, but you were the spark, right? The famous straw that broke the camera's back, right? So these are small little inputs that can change a situation that is already ripe to happen. So I think we are ready for this bull market. All the everybody's anticipating, and I think everything is aligned for the bull market to happen, and it should happen. And maybe the inauguration will be that spark that makes it happen. So I would like to wait for that. So by next episode probably, when is the inauguration? With 20?
On 20, and today is
8. So we will need to wait a couple of weeks before that happens, right? So we will continue to monitor. The only thing, and maybe we can dedicate our next episode to talk about some of these things, is the role of liquidity, because it's still lacking. It is the only thing that keeps me a little bit worried. about having a real bull run right now, because it's the only major difference from everything else that happened in the previous cycles. But we can discuss it next time, how maybe macroeconomic events or factors like liquidity. Did you work on liquidity at all? Did you
Well,
do
I've
any
looked at
study?
it a little bit. There's a great chart from Michael Howell that shows
Right.
the relationship between his liquidity index and Bitcoin, and it's a really steep power law. So I
Yes.
think I would like to show that chart, but we'll think about other things around the liquidity
Yeah.
topic for next
Because
time.
and it's worth it to dedicate his own episode, just to liquidity. So maybe this could be next episode. And maybe we can answer this question, then we can conclude. Um, your opinion when you think the top will be in? Stefan, do you have anything on this?
Yeah, I think my opinion is probably a little bit earlier than Giovanni's. Look, um, from the halvings, the average duration has been between 1 year and 1.5 years. So 1 year after the halving would be the end of April this year, right?
Mm-hmm.
So that's sort of the downside case. And the upside case would be 1.5 years. And that would be by end of October, Halloween time frame. So my expectation is, July 4th plus or minus 3 months. That's what my expectation is.
Yeah. In my case, and this is good. This is why it's good to have different approaches and opinion, and they are not too different, right? Because I'm still open for an April top, because, for example, last time we did have a double top, right? So and one day, maybe even next episode, I can explain you this chart that maybe we commented before, but it's my, let's say, blueprint for Bitcoin, if you want to call it. I have this great vision of how the cycles repeat themselves in a very regular fashion. We have this time when we go exponential up, exponential down, and maybe I'm oversimplifying Bitcoin's behavior, but my way of looking at it is not. I don't use the halving as my reference, even if the halving it's there somewhere, but I'm actually using human time, so quarters, maybe like quarter 4. Basically, almost everything seems to happen at quarter 4 every during the cycle, like at the end of the year. So for example, for the last cycle, we did a peak in April for the first time, but then we did have a second peak in quarter 4. And so I'm sticking with this idea that actually they seem to be all aligned to be around quarter 4 of that particular year, and this should be this year. This year is the year when we are supposed to peak. But in my vision, and we will see, right? This next cycle is going to be so critical, because so many people are aware, right? Because until now, if you were proposing the idea of cycles, given that we didn't have many of them, it could be true, it could not be true. Then we had this third cycle was a little bit funny. It kind of confirmed, right? Because when you have 2, you cannot say that is a pattern, right? You need to have at least 3. So because we are excluding the first bubble, right? Because it didn't follow this 4-year cycle. It also happened before the halvings. So when we had the 2 bubbles, nobody could say, hey, we had a patterns of bubbles, right? Now that we have 3, it's not much, but it's kind of a statistics, right? And with a 4th, that will really solidify, right? It will say, do we have bubbles? Do they happen in regular fashion? Do they peak in quarter 4? Do they peak in other times? It will actually allow us to zoom in and trying to understand better this matter, right? About cycles and what Bitcoin does in general. So I'm very, very curious on getting the data. And guys, this is why I'm so glad that Stephen is here with me. Every scientist will tell you we are not married to our models or our theories, etc. Right? The only reason we do this is because we want to understand. It's not that there is no ego involved. Humans, of course, have ego, but the way a scientist think about these things is like, look, I'm doing this because I'm trying to understand. It's a framework. It gives me some point of reference. But if something happens that doesn't follow my understanding, I'm excited because it's a new way of thinking and learning. There is something to learn, right? It's exciting when things don't go exactly like you thought that they were going. Of course, with Bitcoin, there are other things we want. We don't want to be excited in the price crashing to very low values. We like to be surprising the other way around. But we are still trying to approach it like if it was a scientific topic, right? So basically, it's not a matter of who is right, who is not right. We want to understand, whatever Bitcoin does, right? I imagine that is your approach too, Steve.
Sure.
Right?
Well, sure. We want to understand. We've seen what's happening. That's why that's why you discovered the power law, and why independently I validated it, and it continues to persist, and all the expectation is that things that have persisted for a while will continue to persist for longer. That's kind of the Lindy effect, and that's appropriate for something that's grounded in technology, and it's grounded in energy, and it's grounded in a whole system of networks. It's not a single network. There's at least 10 or a dozen networks that are involved in the total Bitcoin ecosystem. So there are fundamental reasons to expect power law behavior to emerge.
Exactly.
And we monitor it and we see if it persists, and our expectation is it will. Our expectation is we get another nice bubble this year. And, I don't know what your feeling is about the top. I think it's probably in the 200 to 250 range, but
I have the same prediction. Yes,
yeah.
Exactly. Yeah. All right. Thank you so much, guys. It was a pleasure, like always. Thank you, Steven, to be a fantastic co-host. And we will see each other next week.
Thank you. Thanks, everybody.
Bye, everybody.